conservative vector fields. Now, first thing that you have to understand is that if I have a function of x comma y, let's think about an example, say 3x squared y. Then its gradient becomes a vector field. Let's see why. It's, if I differentiate this by x, it's 6xy. If I differentiate this by y, it's 3x squared. And as you can see, this depends on x and y, right? So it's a multivariable function, but its value, the output, is a vector, because if you pick any value for x and y, it gives you back a vector. So for example, what is gradient of f at 1, 2? If I plug in 1 and 2 here, that's 6 times 1 times 2, which is 12. If I plug in 1 here, that's 3 times 1 squared, which is 3. So you have a vector at a given point. So at any point in the plane, you end up with a vector, which means it's a vector field. Right? So you have, from any scalar function, so any multivariable scalar function, taking the gradient gives you a vector field. Okay. Now, here's an interesting question. Does all vector field arise from gradient of some scalar function? And the answer is no. And the reason the answer is no is because we know that if you have this as the derivative with respect to x, and if this is a derivative with respect to y, then the following is true. fxy is equal to fyx. The partials commute, right? If you take a function and differentiate by x first and then y, the same as differentiating by y first and then x, right? So that has to hold, and of course it does hold in this case, right? If you differentiate this by x, you get 6y. No. If I differentiate this by y, I get 6x. If I differentiate this by x, I get 6x. So it does hold, right? So in other words, if I'm given some arbitrary vector field, and somebody asks me, is this from some scalar? Is this a gradient of some scalar? The first thing that I would check is do the following. Take the first thing, differentiate by y. Take the second thing, differentiate by x. And then ask, are they equal? If they're equal, what do you know? Well, it's probably. Okay? Actually, here's an amazing theorem by Poincaré. Theorem. He said that if a vector field is given as two functions at ux comma y and vx comma y, and if you take the first thing and differentiate by y, and if you take the second thing and differentiate by x, and if they're equal to each other, then there is some fx comma y so that the given vector field is the gradient of f. In other words, if ui is equal to vx, then it's a gradient of some scalar function. That's proved by Poincaré's, actually it's called star-shaped theorem, and it actually has one more condition, that this has to be continuous smooth over some star-shaped domain, and but we don't care. Okay, so there's some condition. Okay, it's a non-trivial theorem. Okay? It's kind of interesting that if you have, if you take this, differentiate by y, and if you take this and differentiate by x, if they are equal, then it must be this. Now, for 3 dimensions, you can ask the same thing, right? If you had u, v, w, all functions of x, y, and z, how would you know that it's a gradient of some vector? It's a gradient of some scalar function. Well, you're thinking of this as f differentiated by x and f differentiated by y and f differentiated by z. So you actually have to check 3 things. So I have to know that this is true. And I have to differentiate v by z and then w by y. This has to equal. I'm just writing all the conditions for the second partials to commute, right? Just think about this as fx, fy, fz, and write down what this equation means. It just means this condition. The second condition just means fyz equal to fzy. And then for these 2, you would write down what? Let me see if you understand what I'm trying to explain. For these 2, what conditions should hold? uz, right? And wx. Right, that's correct. Okay. If that's true, then Poincaré's theorem again says that there's some function fxyz. Actually, this f is gradient of some 3-variable function. Now, another way to state this theorem is the following. You remember the curl of a vector field, right? So if you recall the curl of a vector field is what we call nabla cross f. Right? And that's exactly u y minus vx comma, and then I think it's wx minus uz, comma, and then vz minus wy. That's the curl. Okay? And this being, all these conditions mean that this is 0, this is 0, this is 0. Okay? So another way to state these conditions is if curl of a vector field is equal to 0, then f is a gradient of some function. That's another way to state it. And it's a rather simpler condition that you can remember easily. Okay? You don't have to figure out what derivative should be which one. Okay? And for those kind of gradient vector fields, for some reason that will be apparent later, we're going to call them as conservative vector fields. Okay? So that's the definition.